Hey, Algebra 2 honor students, today is the start of Unit 13, and it is day one, which is going to be some intro to trigonometry. And in fact, the next few units of our course are all very heavily related to what we're going to start talking about today with trig. So trig is super critical for things that you'll do in really every advanced mathematics course that you take. So building strong and solid foundations now will be really important for what you eventually do with trig later on. But to get started, let's talk about some things that maybe you remember from geometry. So first and foremost, when we're talking about trig within right triangles, there might be a phrase that kind of stands out to you, and it happens to be SOHCAHTOA. So if you remember SOHCAHTOA, what we're talking about is the three basic trig functions, and we know that sine of an angle, I'm just going to call it theta, because that's what's given as this Greek letter down in the triangle here. Sine theta would be the ratio of the opposite over the hypotenuse of the triangle. Whereas cosine of angle theta is the ratio A over H, which would be adjacent over hypotenuse. And then finally, for tangent of theta, that's going to be the ratio opposite over adjacent. So if you remember that phrase, SOHCAHTOA, and you remember that these are the corresponding sides that represent the O, the A, and the H. What I want to do is fill in, just based on this triangle specifically, what the ratio for sine theta, cosine theta, and tangent theta are. Now, I'm going to label the sides in a specific way just because I think it will help us later on. That across from angle A up here, I'm going to label the side as lowercase a, and this is pretty typical of what you'll see when we label sides of triangles. That across from an angle, we label that side with a lowercase letter. Across from angle B is a little b. Across from angle C is a little c. If you learned law of sines in the past, this would be something that you should be pretty familiar with. And now that I have those labeled kind of in general, if I wanted to know what is sine of theta, sine is the ratio opposite over hypotenuse. So opposite angle theta is the side across from it, which is little b. And the hypotenuse, of course, is across from the right angle. So the ratio for sine theta would be b divided by c. All right, and then moving on to cosine theta, that would be adjacent over hypotenuse. The adjacent side is the side that's touching the angle. So that would be the ratio of A over C. And then finally, for tan of theta, if we do opposite over adjacent in this triangle, that would be the ratio of B over A. All right, moving on to the example right below it, let's just get a little bit more practice with SOHCAHTOA. We have sine A, cosine of angle A, and then we're going to switch over to angle C here in a minute. But the one thing I'll tell you is that in order to find these ratios, you're probably going to need to know this missing side. And I'm hoping there's something that's jumping out to you right away as far as if you have two sides in a right triangle, how are we going to find the third and final side? How about some good old Pythagorean theorem? Now remember that within Pythagorean theorem, the side that you're looking for right here, okay, if we do a squared plus b squared equals c squared, that's one of the legs. So just don't plug it in for c. Okay, if I call this side little a, let's say, it would be a squared plus 5 squared equals 13 squared. Maybe some of you already know the answer here, but if I keep going, it would be a squared plus 25 equals 169. Subtract the 25 to the other side. Square root, square root. Now, I know that square root would make this a plus or minus, but since we're talking about the length of a side of a triangle, let's just make sure we leave it as a positive value. That length is 12, and maybe that's a pattern that stands out to you. It's called a Pythagorean triple. 5, 12, 13 is a special pattern within right triangles. Now that I have that filled in, I should be able to do the ratios for, let's start with sine of A and then cosine of A. Sine of A, SOHCAHTOA, would be opposite over hypotenuse. So opposite angle A is 12, hypotenuse of 13. And similarly, cosine of angle A, use the adjacent side, which is 5 over the hypotenuse of 13. Okay, when I switch my perspective on the other two, we're looking at angle C first. So maybe you go on this side of your picture and you say, all right, cosine of angle C would be adjacent to angle C, which is 12 over the hypotenuse of 13. Notice how these two have the same answer. There is a special relationship there. And then finally, tangent of C would be opposite over adjacent, so that would be 5/12. Okay. So hopefully some right triangle trig, especially when you know all three sides, they're pretty easy for you to fill in those ratios there. Let's move on to the bottom of the page and talk about some special triangles. This is also something that you would have learned in geometry, but I would tell you that these special triangles and the ratios of the sides are pretty important for a lot of what you do with trigonometry. Okay. So I'm going to fill them in kind of in general, and you might remember this pattern from geometry last year, but if you call the side across from 30x in general, the other two sides would always fall into the same ratio, that across from 60 is that value x times radical 3. And then finally, the hypotenuse would be double whatever the side is across from 30. So no matter the size of the triangle, these sides, if the angles are 30 and 60, would always have the same ratio, x radical 3, and 2x. In a 45-45 triangle, since it's isosceles with these angles being equal, these two legs have to be the same. So in general, if you call those both x, the pattern for the hypotenuse is that it would be x times radical 2. Okay. So then from there, if you want to figure out what sine of theta is, given these different values of theta, 30, 45, or 60, we can do that pretty easily just by looking at the triangle, that sine is opposite over hypotenuse. So the opposite of 30 is x, the hypotenuse is 2x, and notice how that since there's an x on the top and bottom, those would cancel and reduce to 1/2. So again, it doesn't matter the size of the triangle. If you have a 30-degree angle, the ratio for sine of that 30-degree angle will always reduce to 1/2, no matter what x is. Similarly, if we look at sine of 45, it would wind up being, it doesn't matter which 45-degree angle you use, by the way, I'll use the one at the bottom, opposite over hypotenuse, that would be x over x radical 2. And with the x on top and the x on the bottom, that would reduce to 1 over radical 2. Now, really quickly here, a lot of times in trig, you'll see that we don't leave radicals in the denominator. So if I can squeeze this in there, we're going to rationalize the denominator by multiplying by radical 2 on the top bottom to get a final answer of radical 2 over 2. Okay. Finally, sine of 60, just make sure you come back to this triangle up here and you do opposite over hypotenuse. The opposite's x radical 3. The hypotenuse is the 2x. When those x's cancel, you wind up getting radical 3 over 2 for sine of 60. And if you follow the logic for these three angles, given the function sine, right, opposite over hypotenuse for every single case, I think if you do adjacent over hypotenuse and then opposite over adjacent, you should be able to try these two on your own. Okay, see what you come up with. They will all eventually not have x's in them when you find those ratios. See what you come up with for the others for cosine and tan within that table down below. And these are very common answers that we're going to get within this trig unit. Okay, so you'll see that come up a lot. Well, if you don't have a special angle like 30, 45, or 60, the good news is that we still have a way that we can find lengths of sides and measures of angles. So to get started with something like number 1 over here, finding the side lengths, if you know an angle on the interior, that this one's 35 degrees. If we think about SOHCAHTOA, we want to choose which trig function makes the most sense to set up in order to find the side length labeled as x. So right now, I would label that the side with x is the opposite side of the 35 degrees, and that the 12 that's given is the hypotenuse. So if we have opposite and we have hypotenuse, definitely I'm going to be sticking with sine for this example. So I'm going to say that sine of 35 degrees, sine of theta, which is 35, would equal the opposite over the hypotenuse, x over 12. And it turns out sine of 35 always has the same value, the ratio of the opposite over the hypotenuse in a triangle with a 35-degree angle. That would always be the same. It has something to do with properties of similar triangles and how corresponding sides are in proportion. So therefore, since sine of 35 is just a value that the calculator knows, it's not a special angle like 30, 45, or 60, but the calculator knows it, we can go ahead and put this over 1 and then think about cross multiplying. X times 1, of course, is x, and then this would be 12 times the sine of 35 degrees. Now we're going to type this into the calculator, but please make sure that your calculator's in the correct mode. Okay, we will eventually be using what's called radian mode. You can see if you have the same display screen as me, that it will tell you at the top what mode you're in. And right now I'm in radian. I need to be in degree mode if I want to type in 35 degrees. If you don't have that displayed at the top, I still want you to hit the button that says mode anyway. Mode is right towards the top next to the second key. Okay, and where it says radian, I do need to switch mine to degree. If yours is already in degree, you're good to go. But once I quit this screen and go back to the home screen, I'm going to type in 12 sine 35 to get that the length of that side is approximately 6.88 units. I'll go to the hundredths place here. Okay, 6.88 is the length of that side. So the great thing about using trig within right triangles is we can use this idea of SOHCAHTOA, fill in the missing pieces, choose the correct trig function, and then be able to cross multiply and solve from there. Now, it's going to look a little bit different when we're finding an angle on the inside. So here's the general process for finding a side. If you're trying to find an angle, the one that's labeled x right here, we're still going to set this up with sine, cosine, or tangent. What do I know this time? I know the adjacent side to x, and I know the hypotenuse. So if I'm looking at SOHCAHTOA, adjacent and hypotenuse definitely is standing out as a cosine example to me. So cosine of the angle x would equal the ratio of 56 over 215. Okay. And then the only difference here is that you're not going to cross multiply. Cross multiplying would not do anything to help us solve for x, because in this case, cross multiplying definitely got x alone, right? But over here, when you're finding an angle, you're going to introduce a new function, which is a button on the calculator. And it turns out that to get x alone, to undo taking the cosine of angle x, we have an operation called cos inverse, cos to the -1. And this might sound familiar from last year anyway. If you do cos to the -1 of cosine x, well, whatever I do to the left side, we have to do to the right side as well. So if I would write cos to the -1 of 56 over 215 here. Cos inverse of cosine x is just x. Okay, so this is the inverse function that undoes the function cosine. So then what I have to do is just type in this ratio on the calculator. To get to cos inverse, you're going to hit second cos. Okay, stick in degree mode. You don't want to change that mode. Second cos of 56 over 215 is 74.9-ish degrees. Okay, so I'll round this to the nearest degree. We'll say that the angle x is approximately 75 degrees. Okay. So it's not that it's that much different. You just have to remember that to find an angle, you're definitely using the inverse trig keys. Okay, if it's at sine x, I would have done second sine to the -1 of both sides. Okay. And we'll get more practice with that as we go through here, but let's move on to solving right triangles. So what I mean by solving right triangles is to find all the missing pieces. So that includes side lengths, angle measures, and everything in between. So if we look at this picture right here, we're definitely missing a few sides. We're missing some angle measures. Because these values are already rounded to the 10th place, I am going to keep everything rounded to the 10th place as well. And the easiest thing to find if you want to really find all these missing pieces is probably starting with this angle. And the reason why is because we already know two of the angles on the interior. So you can do one of two things. You can do 180 minus these two, because of course the sum of the angles would be 180. Or if you remember, these two angles have to add up to 90, right? Because we already used up 90 in this right angle. So these two angles are always going to be complementary. You could very simply just do 90 minus the 47.8 that you're given to get 42.2 degrees is what's left up here. And now that we have that filled in, it doesn't matter which side you find first. Let's say I find the side that's labeled as x first. Okay. To find the side that's labeled as x, it, to be honest, really doesn't matter which of these angles you use. Let's say I use this angle down here, the given 47.8 degrees. I'm looking for x. I know the hypotenuse. So the x side is the adjacent side right now. 89.6 is the hypotenuse. So the way I'm going to set this up is I'm going to do cosine of the angle 47.8 is equal to adjacent x over the hypotenuse 89.6. Okay. Now that I have that, we can put this over 1 and cross multiply, just like I was finding sides up here a minute ago. So we get x equals 89.6 times cos of 47.8 degrees. And rounded to the 10th place on the calculator, let's see what that is. 89.6 cos 47.8 is 60.2 to the 10th place. So we have this missing side right here is 60.2. And finally, for this last side, you have a bunch of options. You can use some more trig. If I'm being honest, I guess you could also do some Pythagorean theorem if you know two sides of the triangle. I'm going to try and stick with some trig here. Okay, and let's see, what kind of trig do I want to use? Let's use, in this last case, if I label this side as y, just pick something else. Let's try and use this angle, the 42.2. And I'll tell you, I'm going to force us into, for this one, let's choose the value of, let's use tan this time. Okay. So if I was going to use tan to find the side that's labeled as y, tan of that angle 42.2, we know is the opposite over the adjacent. So that's going to be 60.2 over the adjacent, which is y. Okay. Now here's the deal. When you cross multiply, for every other case that we've seen so far, we already have the variable alone. In this example, you'll notice that when I cross multiply, the y is still going to be attached to tangent of the angle 42.2 degrees. So the reason why I wanted to set it up this way is just to show you that sometimes when you set up the initial proportion, you don't get x alone right away when you cross multiply, and that's okay. You're just one quick step away. You're going to divide both sides by tangent of that angle to get the value of y alone. Okay, so 60.2 divided by tan of 42.2 is the last step on the calculator, and that's going to be about 66.4 to the nearest tenth. Okay. Now, I tend to not use this side only because I had already rounded it. So when I do that last step, I actually tend to not do what I just did. But I'll tell you, you're not going to get something that's too far off. In fact, when I originally did this, I used sine in the last equation. I did sine was opposite over hypotenuse from this given angle to start. And I still got 66.4. So I'll say that if your answer is a little like off by a tenth, by a couple of tenths here when you do some rounding in the end, it could be based on the trig function that you chose and because we had rounded some other values within the problem. But oftentimes it's going to be super close, or if not exactly the same to the tenths place, like we just saw, if you had used sine instead. Okay. Last new thing that I want to talk about today is the concept of degrees, minutes, and seconds. And this is really the first new thing that you're going to see this year so far with trig, because everything else, if it's looked familiar, that's good news. This is something you would have learned in geometry last year. Okay, so if I had said, hey, come find me in Fairport, New York, and Fairport, New York is at 43 degrees north latitude and 77 degrees west. If you went to exactly 43 degrees north and 77 degrees west, you wouldn't be in Fairport. In fact, I'll double check this in class, but I think you'd be maybe like out by Sodus, if you can picture where Sodus is. So what we have to give a more specific location, right? I mean, 43 degrees north, because of the way degrees of latitude and longitude are labeled, that can be in a wide variety of places, actually. So if we're a little bit more specific of where Fairport is, at 43.0987 degrees north and 77.4419 degrees west. By the way, this is the real information here. What we can do is we can convert that over in terms of degrees, minutes, and seconds. And these types of labels are used pretty commonly when talking about more specific locations than, let's just say, 43 degrees north. Okay, so we break this decimal down in terms of minutes and seconds. And I'll tell you that there's 60 seconds in a minute, and then there's 60 minutes per degree. So this decimal, that is equivalent to what we have with 0.0987. And what I want to do is just show on the calculator how you can take a decimal degree and convert it into degrees, minutes, and seconds. In fact, if you have half of a degree, I already know that for number one, it's pretty easy. It's going to be 22 degrees and 30 minutes. And I'll show you how the calculator can do that for you if you're unsure. So 22.5, if you type that in, you're going to go to second apps. Apps is purple on my calculator. You'll see right above it, it says angle. Okay, so second apps brings you into this angle category. You're going to see degrees, minutes, and then choice 4 is DMS. Degrees, minutes, and seconds. And that's what I want to do. I want to convert this into degrees, minutes, and seconds. If you hit enter and then hit enter again, wow, look at me, Mr. All I knew it, 22 degrees, 30 minutes. And since 0.5 is such a nice decimal, there are no seconds to go with that. Well, if we get something that's maybe a little bit more involved in terms of the decimal here, we'll talk about how we're going to do some rounding. And it does say round each to the nearest minute. So that last value, if it's there, will be in terms of seconds. Let's try 1, 2, 3, 4, 5, 6. 123 degrees, 0.456 degrees. That sounds like a fun one. All right, so if I go to second app again, second purple button, choice 4 is DMS. There are 123 degrees, 27 minutes, and 21.6 seconds when I convert that from a decimal to degrees, minutes, and seconds. So I'm going to write this as 123 degrees, and to the nearest minute, we'll say 27 minutes. So I'll have to think carefully, how should I know if this should round up to the next minute or not? This one doesn't. Let's see what happens in the last example. 43.0987. Second apps, choice 4, degrees, minutes, seconds. Oops, I hit it twice. 43 degrees, 5 minutes, and 55.32 seconds. I'll tell you that this to the nearest minute is 43 degrees and 6 minutes. Now, did it round up because this was a 5 and 5 or more rounds us up? The answer is no, not necessarily. The reason why this rounded up is because this is more than 30 seconds. 30 seconds is now the boundary because, again, 60 seconds per minute. If we're going to round up to the next minute, this has to be 3 seconds or more. And that's a weird thing to think about when rounding. We're so used to 5 or more, bring this guy up. But in this case, it's really 30 seconds or more that we're looking for to round this to the next minute. Okay, let's do a little bit of practice with degrees, minutes, and seconds. This is solve the triangle below. We did a solving question earlier. We were actually given an angle already, so we want to find this angle right here. Now, remember, the way I did this earlier is I knew that these two angles added up to 90, right? So I can do 90 minus. Here's where we're going to type in 32 degrees, 10 minutes. So I'm going to type in the 32 first, then go to second apps and choose option 1 for degrees. Type in the number of minutes, which is 10. And then go to second apps and choose option 2, which is minutes. So hopefully that wasn't too fast. Rewind it if you need to. But if you hit enter, it's going to give you the decimal equivalent, 57.83 repeating. All right, let's see if we can go ahead and convert that to degrees, minutes, seconds. Oh, there's the bell. Don't worry, I'm not quite finished yet. All right, let's go to second apps and choose option 4, which is convert to DMS. So when I do that, it tells me 57 degrees and 50 minutes. And maybe you could have figured that out without doing all that on the calculator. If you add 50 minutes on here, that's going to bring it up to the next degree. So now you're at 33 degrees. And then 33 plus 57 would get you to the 90 that we're looking for. So maybe you can do that in your head if you have a pretty good understanding of what's going on with degrees and minutes. But if not, here's what we did on the home screen to make that happen. Okay, let's see if we can do some trig to find these missing sides. Let's say I want to find this one first. Call this one x. I'm going to use some tangent because I have opposite that I'm looking for and I know adjacent. So let's do tan of 32 degrees, 10 minutes. That would equal opposite over adjacent, 53.1. All right, go ahead and cross multiply. X equals 53.1 times the tan of 32 degrees, 10 minutes. And the way you're going to type in this angle is exactly how I typed it in a minute ago on the calculator. Okay, I'm going to do this a little bit quickly. So it's 53.1 tan of 32, second apps, choice 1 for degrees, 10 minutes, second apps, choice 2 for minutes. And it turns out that that is 33.4 to the nearest 10th. So this side is 33.4. Okay. I'm going to call the hypotenuse y, and I'm actually going to use the same initial angle and the same side that's given. So now if I'm using this side and this side, that would be cosine of 32 degrees, 10 minutes. That would equal adjacent over hypotenuse. So adjacent 53.1 over y. Go ahead and put this over 1. Cross multiply. Okay, this is one where when you cross multiply, the value of y is not by itself right away. So we do have to divide in the end by cos of 32 degrees, 10 minutes to get y alone. And then let's see, 53.1 divided by cos of 32 second apps degrees. You're going to get really good at this eventually about finding those buttons really fast. And then 10 minutes is 62.7 to the nearest 10th. Okay. So if you get those answers that are off by just, let's say, like if you had 0.8 or 0.6 because you used a different trig function, that's okay. As long as you don't use the same exact trig function as me and round incorrectly. If you're off by, a tenth here or there, it's not a huge deal. It might just be that you use a different trig function to set up your equation, okay? There is one more page in the notes, and it's about angle of elevation and depression. I think we'll start with this next time in class. So I'll save the example with elevation and depression for class. This is something that you would have learned in geometry, so maybe it will sound familiar once we go over it. But that is it for today's lesson on our intro to trig. So much more trig to come. I'm so excited. It's a great unit. Have a great rest of your day.